Morning, folks. Hi, and welcome to lecture whatever this number is. I don't know. All the days are the same when you're teaching from an infinite white void, staring into the cold blackness of a camera lens. Although, with that said, there are some things on the horizon I'd like to remind you of. Specifically, next Friday, October 23rd, will be our second exam. To that end, I would expect a couple of announcements made about that on Brightspace here today, if my schedule allows it. I have some time actually this afternoon, so my hope is that I will be able to get to it then. This will include some updates as to the format. I will go through some of them right now. It is, unfortunately, we're not going to be able to implement as many changes as we'd like, just given the nature of sapling learning and the limitations of the platform. But we have done a few small quality of life improvements that hopefully will smooth things out. And there will, of course, be a PSA on academic integrity, and the results of that first exam will be summarized in that regard. So expect updates on all of that today. As far as the exam format is concerned, I recognize that the idea of having to fill in a number for every problem before you submit is a little bit not fair. I mean, it's on the border, right? Because you wouldn't have multiple attempts on a regular exam anyway. So it's reasonable to ask that you have a sort of little higher degree of completion before you submit. But still, it would be nice if you didn't have to do the work for, let's see, what was it, something like 12 different parts of a problem on one of the exam problems, and then you submit them and it turns out you just got one right, so you got to go redo the other 11. That's probably overkill. So what we're trying for exam 2 I don't know how this is going to work. Again, this is all just kind of a new wild frontier. But what we're going to try for exam 2 is we are going to reduce the number of parts that each problem has, and we're going to offset that just by increasing the number of problems by 1. So instead of 3 problems with 10 parts apiece for 30 parts or whatever it was, it will be something like 4 problems with 6 parts and 24 will be the final result, something along those lines. I need to go back and do the exact counting, but at least that's the mentality. We'll have to see how sapling digitizes the problems. I could be saying this and then they could choose to digitize it in a weird way that results in something that wasn't what we intended. Unfortunately, that's out of my hands, but we are cognizant of the fact that it seems insurmountable when you have such a long problem and you get marked off for as many parts as you might. With that said, the intention is the length of the exam is still going to remain the same. Now, we did talk, Professor Mueller and I did talk about the length of the exam and whether or not we could justify shortening it, given that it did take many of you the full 3 hours. Unfortunately, I think just given the fact that this is effectively an open notes take-home exam, there's very little way we can justify making it shorter without just making it all harder. Like, we would have to get rid of all of the easy parts and just give you the hard parts. And I don't think that's fair either. So we're going to see if the slight adjustments we made to the difficulty is enough to make the time a little bit more reasonable on exam 2, but we're not changing anything about the sort of overall length. Again, we will sit down and do a post-mortem after exam 2, see how it goes, and we will continue to adjust. I know that online learning is a nightmare for most of you. It is a nightmare for most of us as well. We're not any fonder of this format than you are, but we do know that it comes with a lot of additional stresses that wouldn't necessarily be present in a typical class. So I want you to know that I am aware of this, and I am here to help you cope however I can. So if there's anything I can do to clarify anything, to dispel any issues, shoot me an email, send me a message in the Discord, whatever you need to do, and I will do my best to help at least set your mind at ease and reassure you that I have your back as best as I can. This is, of course, true as long as you are taking the exam with earnest intent. So that's, again, a hark back to the academic integrity problems we had on exam 1. And I want you all to be aware that I will be looking for that again on exam 2. And although folks have not yet heard from me via email yet, I have finally finished writing up all of my reports, so that is going to be coming soon. So keep that in mind. There's a question in the chat, when's the next exam? This is just a reminder that the next exam is next Friday. That is October 23rd. At least I believe that's the case. I can double check my, my calendar on Pulse, but that should be the case. It is a week from today. There is a practice material uploaded in the Brightspace. It's already up there in Unit 2. If you go to the Exam 2 section, in the Brightspace, there's a file called Exam 2 Practice Problems, and there are 1,000,001 problem. There are, in fact, 313 pages to that PDF, including all of the solutions, so you have plenty of options. Of course, keep in mind that those were in-class exams, so they were necessarily easier. So take that into account when you are practicing. But, otherwise, don't expect any changes from the exam other than the ones I've already went over. All right, with that said, we are 6 minutes in, and let us now turn our attention back to what we were talking about before, which are resistors. This is a new type of circuit device that we're going to be talking about quite a bit over the next few days. Well, I should say next week. Let me just get some of this coffee out of the way so I don't spill it all over my very makeshift setup here, which is a folding TV tray and like a weird home entertainment riser that's crooked on one end, and a podium made out of a monitor stand and some pieces of wood that I chopped up. This is a mess, guys. I'm so sorry. Where was I? Resistors, material and device properties. This is the stuff we talked about last class. The idea that when you have a conductor that is not in equilibrium, you apply, say, a potential difference to it that will produce an electric field. That electric field will in turn produce a current density in the wire, which is related to the overall current through the material. We quantified the behavior of conductors and according to their resistivity, which is related to their conductivity. And all of this stuff up here, electric field, current density, resistivity, conductivity, and the relations between them, these are all material properties. So these are things that you might apply, say, to copper or tungsten or, aluminum or something like that. So this is applied to the material. In this unit, we're actually, generally speaking, more likely to be talking about the actual devices we make from these materials. So that is to say, the resistors that we would attach to a battery. Now, these resistors have a much more simplified way of expressing their relationships to the various properties of a circuit. We specify the amount of voltage applied to a resistor. That's generally provided by a battery, but we'll see that's not the only case. The electric current is I. That is the total amount of current that flows through the circuit. The amount of current will be related to both the voltage and the resistance, which is the property of this specific device, through Ohm's law, V equals I times R. Or written here, R times I. Doesn't matter. Commutative property. We can, of course, relate the material properties to the device properties through the relationship between current and current density. Same way we can relate voltage to the electric field, but broadly speaking, we won't be doing that too much. We're mostly just focused on the actual circuits and their properties. So today we're actually going to be talking about sort of what these resistors do, what their role is, what their function is, and we'll spend the remainder of our time analyzing circuits that involve resistors. Now, put simply, if a capacitor's purpose is to store charge, a resistor's purpose is to take current and do something with it. Now, the thing that it does is actually very straightforward. It converts electrical current into power, specifically power in the form of heat. This may not seem like a particularly lofty purpose for a device to have, but it is the general role of these things to just turn electrical energy provided by a battery, generally speaking, into thermal energy. Of course, they have many other applications. You can use it to control the amount of current to very fine amounts. You can use it to damp down certain behaviors that you don't want to see or spike up behaviors that you do. But when you actually get current running through a resistor, the only thing that happens, other than the fact that current is running through a resistor, is that resistor starts to heat up. And we can quantify how much power, how much energy, is dissipated in a certain amount of time by just analyzing very quickly what's happening in a simple circuit like this one. Now here we have current going into a resistor. So we can specify the voltage difference, or I should say the voltage, between each end of the resistor simply by looking at the voltage of the battery. We consider wires to be ideal conductors, so their resistance is 0, which means that the voltage stays the same everywhere in the wire. So whatever the voltage across the battery is going to be the same as the voltage across AB here. And we can specify that in terms of the electric field and the physical distance between these 2 points. Now, once we attach this battery, the thing that's going to happen is a little bit of charge that's in that wire is going to feel a force from the electric field, and it's going to be displaced by a certain distance. We're just going to see the charge moved by the force that is applied to it. We can specify the change in charge, meaning how the charge changes from here to here, simply by from our definition of current. That is to say, that's not the right. There we go. Current is dq dt, such that by separation of variables, I dt equals dq. And when these are finite non-infinitesimals, you can turn this dt into a delta t, this dq into a delta q, and that's just the relationship right here. So what this allows us to do is specify the amount of charge that is subject to the motive force from the electric field. Once we know how much charge is there, we can calculate the work done by the electric field moving said charge that distance. That is to say, how much energy would it take to move the charge Q from this point to this point? Work for one-dimensional applications is just force times distance. The force is E times Q. Note that E times this displacement here is just what we wrote up top. So that means this is Q times the voltage, V. And so we see that the work done is just V times our charge, which is V times our current times delta T. In case this is not clear how we got here, we took our force, plugged in our definition of force, F equals QE. Then we took advantage of the fact that V is equal to E delta X. And then we took advantage of the fact that delta Q equals I delta T to get to our final result. Now this is useful because now we have an expression for the work. V times I delta T. But of course, we can divide both sides by our time interval. Note that that causes those to cancel out on the right. And we have energy divided by time. Well, work done divided by the time over which that work was applied, that's just the power. So that's what we have here. So we see that the power is equal to V times I, the voltage across the resistor times the current through the resistor. Now, it turns out this relationship is very general. V times I is a form that you can use to calculate power for any circuit device. But if we are talking specifically about a resistor, we can take this expression and we can plug Ohm's law in to get two additional versions. I squared R, that's when we replace V with IR. And then V squared over R, that's when we replace I. These three equations, oops, I want to make that red. What the heck? Technology, I miss a whiteboard. Okay, these three equations are all equivalent ways of calculating the power dissipated by a resistor. And it is worth noting that if you actually go through the process of checking your units, doing dimensional analysis, sure enough, no matter which one of these equations you look at, we end up with the unit being a watt, 1 joule per second. So this is precisely what we're used to when we're talking about power. So this is the amount of power used up by the resistor as current is flowing through it. Let's try a couple of quick applications involving that. Now, for this problem, I'm going to go ahead and just write down my different versions of power, because which one of those equations you use just depends on which problem, or rather what numbers the problem gives you. Here we have a heating element that's made up of a wire with a cross-sectional area that's given to us and a certain resistivity. If that element dissipates, say, 5,000 watts when running at a certain voltage, we want to know what its physical properties are. Its length, its resistance, and the current running through it, and so on. Now, this is an example where this is not exactly plug and chug. We're not asking for the power. We're also not given the resistance. So we've got a lot of stuff going through here. So let's just analyze what we can based on what we're given. Now, we're told the cross-sectional area, and we know the resistivity, and we're given the power that is this particular wire is dissipating. So let's start off with P and see if we can solve for any of the unknown variables. Well, we're given voltage, so it stands to reason that we want to use that to find out something else about this. So we can use either I times V to get the current, or V squared over R to get the resistance. Either is fine. We don't really know what we're doing quite yet, but it turns out, if we look at this, both of these, current and the resistance, they're both things that the problem wants us to see, or wants us to find. So we can start with either of those. Now, P divided by V to get I is probably the most straightforward one. If I just take 5,000 and I divide that by the voltage that's given, that's 75, that gives me a current of 66.7 amps. It's worth noting that that current is pretty large. If you recall our discussion before, a typical household circuit has a maximum current of, say, 15 or 20 amps. So whatever's doing this is quite a bit, is taking quite a bit of juice. Now, we could also find the resistance by doing V squared divided by P. So that is going to be 75 squared divided by our power, 5,000. That's going to give us 1.125 ohms. It's worth noting that we could actually do a little sanity check at this point by taking these two results and confirming that they give us the appropriate amount of power. Theoretically, if I take I, square it, and I multiply that by R, I should get the power output. Now, I'm going to be careful. I'm going to use the unrounded current. And sure enough, when I do that, I get 5,000 watts, which is exactly what I would expect in this scenario. If I didn't get 5,000 watts, that would be an indication that I had done something wrong. Now, from here, we actually have 2 out of the 3 things that the problem asked us for. We have both the current and the resistance. Now, the thing that we still have left to do here is calculate the length of the wire. And that's where the actual physical dimensions of the device are going to be needed. Yeah, okay. Just double checking. So for the length of the wire, we want to use the fact that the resistance is related to our resistor design equation. Resistivity times length divided by area. We can rearrange this, R times A divided by rho, to give us L, which is the last thing that we need here. Thankfully, we have all of these values now. 1.125. Area is 2.60 times 10 to the minus 6. That's already been converted to meters squared. And so then we just need to divide by the resistivity. 5.00 times 10 to the minus 7 ohm meters.
It's worth noting that just if I do the dimensional analysis here, so I'm actually going to be careful. I'm going to write out my units. Give me a second. I have ohms, meters squared, ohm meters. Note that ohms will cancel with ohms, meters will cancel with one of my meters, and I'll be left with just meters, which makes sense. We're solving for a length. That's what we should have here. So if I plug in everything, 1.125 times 2.6 times 10 to the minus 6, and you'll want to be careful when doing the scientific notation in your calculator, but when you plug all of that in, we should get 5.85 meters, which is actually a rather long cable, right? That's something on the order of probably 20 feet. And so it's a 20-foot long extension cord. So note that that would be dissipating quite a lot of power. Now, if you were to do problem B here, we want P to still equal 5,000, but now we want I to be half of our current, so that would be 33.3. And we would just repeat the process with these values, and I encourage you to give that a shot on your own. The answers are in the notes. Here is another problem. This one is maybe a little bit more applicable to sort of an actual application you might be familiar with. We have a 1250-watt radiant heater that's constructed to operate at 115 volts. This is, in fact, precisely the sort of space heater that you might, say, plug into a wall when it's cold to warm up a room. In fact, this is an actual application of certain types of resistors, is to just generate power in the form of a heater. If you, in fact, have a water heater in your house, it's probably doing the same thing, using just a big resistor to generate a lot of heat with current going through it. Now, in this case, we have a 1250-watt radiant heater that's constructed to operate at standard household voltage. We want to know what the current in the heater is, the resistance of the heating coil, and how much thermal energy is generated in 1 hour. Now, part A and B here should be straightforward based on what we've talked about so far. I know that, might help if I had my pencil selected, P equals IV. So the current is going to be P divided by V. That's 1250 divided by 115. So no surprises there. 1250 divided by 115 gives me 10.9 amps. The resistance can be found by V squared over R. This is the exact same process we went through before. Oops, I'm solving for R, not V. V squared divided by P. So 115 squared divided by 1250 gives me 10.6 ohms. We can just do a little sanity check, see what we actually get when we do 10.9 squared times 10.6. And again, I'm going to be careful to use the unrounded values just to make sure everything works out. It needs to be multiplied instead of divided. There we go. And sure enough, I get 1250 ohms, 1250 watts, which is a good sanity check. Now, part C might seem a little bit out of nowhere, like how much thermal energy is generated in 1 hour by the heater. This goes back to your Physics 203 content. Remember that power is energy as, with respect to time. So as a general feature, power is dE dt. It's the derivative of energy with respect to time. And that energy can be in a number of ways. It can be work done, like we did before, but generally speaking, that's the relationship between energy and power. And we can get this by rearranging P dt equals dE. And theoretically, how you would actually solve this is you would actually integrate both sides. But for constant power sources, that just works out to P times delta T equals delta E. So the amount of energy generated in 1 hour is just our power, 1250, multiplied by the amount of time. Now, you might be tempted to do 1250 watts times, say, 1 hour. HOR? What is an HOR? I don't know, Professor Coyne.
What is that? Except this will not work out, right?
Because the reason this will not work out is one of units. Watts are joules per second.
Seconds don't cancel with hours.
So we actually have to convert 1 hour to seconds. 1 hour is 60 minutes. 1 minute is 60 seconds. And so 1 hour is 3,600 seconds. And so that's actually what we have to multiply down here, 3,600 seconds.
So 1250 times 3,600, again, that should be multiplication, not division, is a pretty big number. That looks like
4.5 times 10 to the 6 joules, or 4.5 megajoules.
Just double check that I didn't do anything silly here. Nope, that's correct. It's worth noting that there is, in fact, a commonly used unit that allows us to bypass this dimensional analysis, this conversion of hours to seconds. In fact, it is so common to measure power in watts and time in hours that if you look at your electricity bill,
what you will probably find is that your units
are so-called kilowatt hours.
If you convert 1250 watts to 1.25 kilowatts, and then you multiply that by 1 hour, the result is 1.25, and then the units that we get are kilowatt times hours.
Kilowatt hours are a very commonly used unit in practical day-to-day electricity. So in fact, if you ever look at an electric bill, it will almost assuredly report your usage somewhere in terms of kilowatt hours. That's literally a measure of how much energy did you use from the power company. And that's what you're billed for. So you'll often see things are, at a cost per kilowatt hour. Of course, in this class, we're interested in scientific notation, so we'll want to report our units in joules. Okay. Enough of the power dissipation. We're going to spend the rest of the day talking about circuits that involve resistors. Now, a couple of quick things that I would like to point out. No, why is my... There we go. Sorry about that. A couple things I'd like to point out. In the real physical system, what we'll do is we'll take, say a battery, and we will connect the two ends of a battery to a wire, and that wire will have a shape and size, and there will be devices attached to it. So for example, I might take a wire and connect it to the physical ends of the battery, and there you go, here's my physical circuit. It's a pain in the butt to actually draw all of the details of that, so we use symbols. So this is a so-called circuit diagram, and we use the symbols representing the different components in our circuit diagrams, and this simplifies the process a little bit. The battery is, again, two lines, one of which is longer than the other. The longer end of that battery, if I'm just going to zoom in here, represents the positive terminal of the battery, and the short end represents the negative one. If you've ever looked at a battery, and I don't think I'm going to be able to zoom in close enough to really show you this. Oh, maybe. Yeah, that's actually kind of clear. You may have seen that batteries are marked with a plus end and a minus end. That is indicating the so-called polarity of the battery, and we make a note of that in our circuit diagrams. Now, resistors do not have an intrinsic polarity. Their polarity is based on whatever current is running through them. The idea being that as you're going across a device, the polarity indicates whether you are gaining energy or losing energy. So here, as I go from B, I start at the negative side, and I come out on the positive side. So I've gone from negative to positive. I have gained energy. My value has, my voltage has increased in this direction. So that, following along the direction of the current, will get to the resistor. And the idea for resistors is that the current goes in on one side,
and the resistor uses up some of that energy, so the current comes out on the negative side. We're going to get more practice indicating polarities a little bit down the line. This is a sort of visual trick that I like to use to keep circuit analysis simple. Broadly speaking, all this really means is that the resistor uses up energy, so the electric potential goes down through the resistor, and it goes up through the battery. That's all. It is worth noting that the total change in voltage as you go around a circuit has to be 0. This should make sense. Think about it. If I start at B, let's say B is, I don't know, 0 volts, and I gain 10 volts, I then should have to lose 10 volts, so when I get back to where I started, my voltage is the same as it was to begin with. This is the so-called loop rule, and it's expressed as follows. The sum of changes in the potential encountered as you complete a closed loop in a circuit must add up to 0. So the sum of all the voltage differences in a closed loop have to be 0. We're going to get lots of practice with this. As a brief sort of academic aside, it's worth noting that this is an idealized battery. The idea is that the only thing that the battery does is produce the voltage that is used up by the rest of the circuit. In actuality, wasn't zoomed out far enough. In actuality, batteries are like physical devices, meaning they're not perfect. Yes, they produce an EMF, but they also have some internal resistance in them. They're not perfect devices. They don't have resistance equal to 0. And we can actually represent that in a circuit diagram. In fact, we could even represent a non-idealized wire simply by adding another resistor in the circuit. That resistor would be between the terminals of the battery. So in the space between terminal A and terminal B, we add an extra resistor. And this extra resistor just represents whatever intrinsic resistance is inherent to the battery. Now, note that this has a couple of features here. One, although the battery still produces the same amount of total EMF, the internal resistance decreases that a little bit. So the practical voltage that the resistor experiences, that is to say the voltage between B and A, is a little bit smaller. Because as I go from here, I gain however much is provided by the battery, but then I lose a little bit from the internal resistance. And that's represented on this diagram. Note that a full path around, I still have a full, there's a question in the chat saying that apparently my audio is cutting out a little bit. I can try to restart the stream here if that's an issue. Just give me a split second. Alrighty. All right, I don't know if that helped or not. My little microphone pack is bright green, so I'm not running short on battery. If other folks are having audio issues, could you just throw them in the chat and let me know, and I can try to adjust. In the meantime, I'm going to continue on since that's the only comment to that effect that I see. Where was I? Right, that as I go around the whole circuit, so let's say I start here, I lose the amount according to Ohm's law, IR, I gain the amount E provided by the battery, I then lose the little amount to the internal resistance, but note that the voltage I end up at is the same at the voltage I started at, so my loop rule still applies. Note that I can see this explicitly if I come down here and I label all of the polarities. So the battery has a set polarity, and resistors use up energy with the direction of current. So the current goes in on the positive side and goes out on the outside, on the negative side. And now if I just follow this around, I see I go from negative to positive. That's a gain, then a loss, then a loss. I gain E. I lose IR according to Ohm's law. I lose IR according to Ohm's law. Note that I have one of these terms for each one of my resistors. Then I'm back to where I started, so I know that the total sum has to be 0.
that's the process we're going to practice for the remainder of class today. It's worth noting I have a few example slides. And we're just going to get through as many of these as possible before the end of the class in 15 minutes. And that's what we're going to be doing for the rest of the time. OK, it sounds like other folks can hear me OK. Sarah, if you're still having issues, you might want to try to just refresh your YouTube stream. Okie dokie. Where was I? We're doing, yep, this one. OK. So here is a voltage circuit, and we're going to start getting into a habit that's going to help us a little bit later on down the line. And that is by following this algorithm for approaching circuit diagrams of all types. First, we're going to label our current direction using our intuition. There are no real right or wrong answers here. The math will be self-consistent even if you guess the direction of the current wrong. This will not be a big deal in this particular section. We're basically always going to guess it right. But next week when we get on to advanced circuit analysis, we're going to see that this process of labeling currents is much more important. So I want to get out ahead of it now. And generally speaking, current comes out of plus side of battery. So remember, batteries have a positive side that is indicated by the long line, and a negative side indicated by the small side, and current always comes out of the positive side. So right away, this allows us to say what the direction of the positive current is. So this would be the direction of the current if the positive charge carriers were the thing that were moving. Fun fact, if you are annoyed by the idea that the direction of the current is actually opposite to the direction that electrons flow in the circuit, you can blame Benjamin Franklin for that. Way back, in the key and the kite days, where Benjamin Franklin was doing early experiments with electricity, he recognized that there were two types of charges. He didn't know what they were, so he just had to label them. And he had two options. You pick one and label it positive, and pick one, label it negative, and those would be the two charges. And so he said, the thing that looks like it's moving, I'll call that the positive charge, because I get to choose, and I have a 50% chance. Well, it turns out the positive charge isn't actually the thing that's moving. So even though the current is this way, and the electrons would be going in the other direction, we still use that convention to this day. Just a little piece of historical trivia for you. All right, so we've labeled the direction of our current. And in this case, note that this means the current is going to go around the circuit this way. That is counterclockwise. So that is going to be the answer to our direction of the current. Now we need to find the magnitude of the current. And now before we do that, what we want to do is label polarities of all devices. Remember, current enters resistors on positive, exits on negative. This is not going to be super useful for these very simple circuits, but again, I'd like to indicate that this is a habit we're going to want to get into. So current comes out, comes down, goes in on this side, positive, leaves on this side, negative, continues around, comes in on this side, positive, leaves on this side, negative, continues on, comes up, enters on this side, leaves on this side, and we're back to where we started. So now the polarities are labeled. Then we are going to start applying our loop rule. That is to say, we're going to walk around the circuit, and we're going to add up all of the changes in voltage.
whenever there is a battery, that will add plus or minus the EMF. Resistors will add plus or minus IR according to Ohm's law. And the sign will be indicated by the polarities involved. If I go from negative to positive, that is a gain, therefore I will add the voltage. If I go from positive to negative, that is a loss, so I will subtract the voltage. So just to make that clear, from negative to, I'm going to zoom in so I can write this clearly. From negative to positive is a gain. So that's going to add voltage. From positive to negative, that is a loss. So I'm going to subtract the voltage. What? Could you please rephrase that question? I'm not sure I quite understand. So it's worth noting that I think maybe actually I do understand. These polarities are not positive or negative charges. They're just telling you which side of the device is at a higher voltage. So positive in these polarities indicates the higher voltage side of the device. So this means here that this side is at a higher voltage than this side. These are not positive and negative charges. So this is telling us that the current enters when the voltage is high. The resistor uses up some of that voltage, so it is at a lower voltage when the current comes out. I understand. Yes, so just to further clarify the question, I understood that it was about the resistors, but you asked what does the current enter positive, and I'm not sure what that means. Hopefully that cleared it up a little bit, though. If you could rephrase, and if that didn't clarify, I'll address it again. But for now, we're going to go through the process of going through this loop. Now, I just like to make a little virtual note that I'm just going around the loop in a certain direction. This just is for a little way to remind myself to make sure that I do things consistently. Then I choose a place to start. It doesn't matter where. I'm going to choose to start at point C, but it really doesn't matter. So then I'm just going to start walking through the circuit. I'm going to go from C to D, and note that I pass through my first circuit device. So this is a battery. So I'm going in this direction, so I go from negative to positive. That is a gain. So I'm going to add the voltage of that battery. Now in this case, I'm actually given numbers, so that's going to be plus 12 volts. So this comes along. I get to D. I'm continuing along my path. I'm coming down through B. I go through a resistor. I go from positive to negative. That is a loss. And I'm going to lose my voltage. That is I, which is unknown, times R, 1 ohm. I continue this process around. I go from B to A. I go from positive to negative. That is a loss. It's the same current, I, still unknown, times 2 ohms. Come around. I go through the last leg of my journey from A to C. It's another loss through a resistor, positive to negative, minus I times 1 ohm. And now that I'm back where I started, I know that I'm done, and those have to add up to 0. So at this point, I'm just going to factor out my current. 1 ohm plus 2 ohm plus 1 ohm equals 0. So this is 12 volts minus 4 ohms times I equals 0. Rearranging this will give me 3 amps for my current. And so now I've found the magnitude of the current by using the loop rule. Now the individual voltages, VA and VB, or rather VAB and VCD, can be found in a very analogous way. I can walk through the circuit,
and I can take a path through, and I will just add up the voltage differences. So for example, if I want to do from final minus initial, so this is the voltage going from point A to point B, I can just start at point A, go to point B, and figure out my voltage change. These are always final position minus initial position. So this is saying I start at A and I go to B, which means I'm going in this direction. Worth noting that this is why polarities are useful. Because as I go from A to B, note that now I'm going from negative to positive. That is actually a gain. So positive I times 2 ohms, and I just figured out what the voltage is, or rather what the current is, so that is going to be 6 volts. And note that that is a positive sign. Alrighty. I could do the same thing going from C to D. Final minus initial means I'm going this way. And note that that is just going to be the 12 volts of the battery. Note that because neither of these paths are closed, these are just lines, these voltage changes do not need to add up to 0. They can be just whatever it is. It only has to add up to 0 if I end up back where I started. Now, unfortunately, it took us a long time to go through that, so I'm going to leave this page largely as an exercise for you. I do want to mention, though, that we have to figure out what is going on with these multiple batteries, because it's easy to figure out the direction of the current when there's only one battery. When you have a whole bunch of batteries, that's harder. Now, the good news is that you don't actually have to guess right. You can just pick. I could, for example, say that this is the direction of positive current. As long as I label all of my polarities according to that, then it's fine. That's why this problem allows you to choose a current direction. There is no wrong answer here. If it turns out you chose incorrectly, if you chose the direction of the current in a way that is inconsistent with the direction it's actually flowing, that's fine. You'll just get a negative value. When you solve for I, it will be negative, which just indicates that you labeled it in the wrong direction. And there's nothing wrong with that. It's totally fine. You can, however, kind of analyze the circuit and take a guess if you would like. Note that these two batteries are oriented in the same direction and add up to 36. These two batteries are in the opposite direction and add up to 24. So it's probably reasonable to say these two batteries overpower these two batteries. So it would be reasonable to infer that the current is actually going in the opposite direction of what I've labeled here. Sure enough, if you go through this process, you will find that the number that you get would be negative in this case and positive in the other case. And as long as your answers are consistent with your diagrams, it really doesn't matter what direction your label is. But you still just want to follow these same steps here and analyze it in the same way we analyze this circuit. This is worked out in the notes, so I encourage you to go give this a shot on your own time and compare against the final results. Because we are a little bit behind on time, I think I would like to do one more practice problem here. I'm not going to have time. We'll see. But what I will say is there are two more slides that I need to cover with content. The first is this one here, and it's very straightforward. Basically, it just talks about how power is used in a circuit. And there are two ways for this to work. If the battery is in use, meaning the battery is providing the energy, then our loop rule is just going to be the total voltage is going to be dissipated by the resistor. We have the external resistor and the internal resistor. Those are both dissipating energy. The battery generates voltage times current, and the internal resistance uses up or dissipates I squared times R. All of this stuff is the net output of the battery. That net output is what is transferred to the load, which is used up. You can, of course, also run current backwards through the battery, which means that you can charge the battery up by forcing current back through it with some type of charging device. This will allow you to store power in the battery, although you will lose a little bit of efficiency because the battery's internal resistance will still use up or dissipate some of that supplied energy. This is why it's never a perfect scenario. You're always using something up a little bit. You can't get that perfect efficiency between charging a device and storing the energy. The other slide I want to discuss is this one right here. There's a process called impedance matching. If I have a real physical battery, and this means it has an ideal EMF and some internal resistance, then the current that we get out of it is the total voltage divided by the total resistance. This is going to lead to a sort of interesting scenario where if we calculate the power delivered to this external resistor here, so it's I squared R, I plug in the current supplied by the battery into this expression, and I get this complicated expression here that is a function not only of the battery's voltage, but also the ratio of the resistances involved. This actually indicates that there is a maximum amount of power that you can extract from an idealized battery. We can find that maximum by using simple calculus approaches. We take the function for our power, and we take its derivative as a function of the thing we're trying to optimize. We want to find the maximum power as a function of the resistance we attach to the battery. So we take our derivative of power with respect to R, and we set it to 0, because wherever the function's derivative is 0, that represents an extrema. So we can find the maximum value of this power right here, and it turns out that happens when the load that you attach to the battery is exactly equal to the internal resistance of the battery. This is a process called impedance matching, and it optimizes the energy use in a circuit. And if you're, say, a musician, for example, and you're plugging, say, speakers into a amplifier, this process is very delicate, and you want to make sure that you are maximizing the output here. I would love to go through another example, but unfortunately I just don't have time because I do have another class that starts in 7 minutes. I'm sorry it spent so long. Hopefully you found the deliberate steps through that process useful. Before you try the lecture quiz, I'm going to really strongly recommend that you go into the lecture notes on Brightspace and you look at this problem and this problem, because they are both worked out in detail in the lecture notes, before you try this, which is the quiz for the day. So give that a shot. Let me know if you run into any trouble, and we can touch base either via email or through an office hours appointment. Good luck finishing up your homework today. I will be around intermittently throughout the day if you want to shoot me an email or message on the Discord or something, or you want to pop into my office hours. I do want to mention that I am kind of leaving pretty promptly at the end of my office hours, so that is about 3 o'clock. I have a prior commitment that is not at my home, so I will not be able to answer emails late at night tonight, nor will I be able to respond on the Discord in any sort of timely manner. So if you have questions on the homework, I strongly recommend that you ask me before 3 p.m., and I will do my best to get back to you. Otherwise, here's your quiz, folks. Have a great day and enjoy your weekend. I will see you next week.